Good morning, everyone. We are very, very excited about this new lecture series. um, Let me tell you a little bit about the Science of Learning Network and then how this lecture series developed. So the HBCU Science of Learning Network is a collaboration of HBCU faculty from around the nation that we are building and we are trying to grow to approach learning and the learning that's happening within classrooms at HBCUs. And so we're trying to, as we move into a different generation, a change in the way that education is happening, we're trying to, in these classrooms, make sure that we keep up with what's happening and that we are as actively involved in making sure that education is available to our students and they are learning as efficiently as possible. And so I'm very excited about this network. I'm very excited about the work that I'm doing with Ben. So Ben and I also have another research grant where we are actually looking at some of the things that he's going to talk to you about today. We're actually implementing them in some of my classes, and we're looking at some data from classes that have already happened at Bethune-Cookman University to be able to look at some of these learning gains and learning information that we're going to talk to you about today. So I'm very excited about that. And so this lecture series serves as a way for faculty, students to understand what the science of learning is. Because I'm going to be honest with you, when I first learned about this a couple of years ago, when I first met Ben, I was like, Ben, what is this? What's going on here? Like, talk to me about this. And in the conversations with Ben and other faculty, I'm like, this is what I'm trying to do. So I say that to preface by some of the jargon, and as we all know in areas, in our various research areas, and that there is jargon that must be understood. Right? So don't let the jargon scare you. This is most likely what you are already doing in your class. It's just giving you a mechanism to actually measure the learning that's happening. To actually say, my students are learning, right? And I know that is so by looking at this, and this metric. So a little bit about our speaker today. Ben, a good friend of mine, he's been doing research on the science of learning and as a learning scientist and a learning engineer for over 30 years. That's a very long time, almost older than me. Ben is obviously he has a computer science background. He's been working with the leaders in the area of educational tools for science of learning. I mean, he has worked with a number of them from pretty much their entire career. So he is very versed in this, and we are lucky to have him as our consultant and our chief consultant on the network as we work to develop some of the tools that he has developed throughout his entire career. He's going to help us develop similar things within the network. So we're very excited to have him here. We're very excited to hear his talk today. And so without further ado, Ben MacLaren.
Okay. So am I on full screen?
You're not. You have to, if you're going to share your screen, you should have the ability to share your screen now, if you're going to share your presentation.
Video. So, yeah. I don't. How do I go to full screen?
Are you trying to share your screen?
I'm trying to go to full screen. Am I full screen?
What do you mean by full screen?
Well, oh, right.
Yeah, the bottom, there's a green button that says share screen on your Zoom. Oh, you're trying to get your
Well,
Zoom.
I don't want to do that just yet.
Okay.
Um,
The if you go up to your Zoom meeting box.
anyway, I'll get it. So thank you, Albert, for that introduction. I completely agree with Albert that you shouldn't let the jargon overwhelm you. That goes both for the learning science stuff and the content of the biology stuff that I'm going to be talking about. Oftentimes, learning by doing is one of the reasons it works is because you just get past the introductory stuff with all the technical jargon and just jump into trying to do it. And if you scaffold an activity properly, then things just kind of seem to come naturally. So let's try to now I want to get to okay, so now you should see my machine. Okay.
So now we see your PowerPoint screen.
Okay, now I'm trying to get rid of the now you
You want
might
to
if you might be justified in questioning whether I have a master's degree in computer science from Carnegie Mellon. Now I want to, okay.
at the bottom, if you go to the bottom, you see where it says the very bottom. No,
No.
not in there's a little screen button at the bottom of your screen to the right next to where you can change the magnification.
Well, this should be, let me get to slideshow. Are we good now?
We are.
Okay. So, I'm going to talk today about a framework for teaching transferable computational thinking skills in STEM education. And it hopefully is going to prove generally useful for all of STEM education. But this framework that I designed was developed for biology education in particular. So just as an outline, first, we've been talking about why we're here, where we're going. We're developing this science of learning network, and hopefully we're going to convince some people to join us. I want to talk about some of the challenges in STEM education and some of the proposed solutions, and then computational thinking, one of the key ideas that people are pretty excited about, and then briefly about quantitative and, more importantly, qualitative analysis in biology, and then pathways in the biological sciences, which is a very important qualitative model for information flow that hasn't been getting nearly enough attention in education, especially at the early levels of education. And then I'll talk some about symbolic language to represent pathways to support learning and, importantly, transfer between topics. Then we'll talk about some of the learning goals for biology, an important step in the learning sciences. And then we'll talk about a cognitive tutor for implementing that. So one of the reasons I may have stumbled upon some interesting ideas in teaching biology is that I am virtually self-taught. I have a degree in computer science, And I decided to study AI models of scientific discovery in the biology, in the biological sciences. And that led me to just start learning about biology. I literally had just had an introductory freshman course in biology. So I started reading journal articles. I started reading, there's actually a journal where Nobel Prize winning scientists publish a summary of their research. And that was something that I spent a lot of time reading. There was a book by Jared Hudson, a book called The Eighth Day Hodson, a book called The Eighth Day of Creation. If you're interested in the development of molecular biology, I strongly recommend reading that book, The Eighth Day of Creation. You can get a PDF of it free on the internet even. So I'd been doing, as Albert said, I've been doing research, education research, computer-based education research for over 30 years by now. And when my principal mentor that I'd been working with for many years, a guy by the name of Albert Corbett, who was instrumental in developing cognitive tutors, and he started a company for marketing their math tutors called Carnegie Learning that's done quite well. He's a cognitive psychologist, and I worked with him developing cognitive tutors for biology and genetics. He would have various learning theories that he would want to test, and I would develop cognitive tutor lessons for those ideas. And between Albert and Linda Kaufman, a biology professor, and me, we would design these activities, and I would implement them. And then we would put them in front of students and see how they worked. So when Albert decided to retire, I thought that it was time for me in my career to actually go out and start applying this stuff and try and get this tutor that we developed used on a much larger scale. And very serendipitously, that was when I met Raphael Isakpehi, that many of you know as Dr. Iso. And it was actually Sherma that introduced us. And we really clicked. We just really had the same goals, and that led us to where we are today. So let me just talk briefly about what the science of learning is, and how we want to leverage it with your assistance. So just imagine, for the 300,000 students at HBCUs nationally, imagine them learning at a pace that suited them, mastering the material that they were in their classes faster and more smoothly than ever before, with more one-on-one tutoring and assistance than any professor can give to, than any instructor can give to all their students. That's what we're aiming for here. We're wanting to apply the technology that engages students in active learning, and making these material less intimidating and reducing the stress that often comes with education. So we're also here to help the educators. We want to arm you guys with the power of data. We want to facilitate the development of developing educational technology that will allow you to make data-driven decisions to improve your teaching and creating more effective classrooms. It will save you in time on planning and grading, and we want to help you create happier classrooms and reduce some of the stress that you feel for not being able to give your students all of the time that you would like to. So we really want to ease the burden on you, the instructors. We want to make grading easier. We want to encourage you to share, to research and share effective teaching materials. Find collaborators at HBCUs around the country that teach the same, excuse me, courses that you teach, and work with them to develop technology for teaching those classes. You know, if you, the old adage about teaching a man to fish feeds him for a lifetime. Well, if you teach a computer to teach a man to fish, then you can teach hundreds of thousands of men and women to fish. So that's what this is all about. Now, the basic process behind the science of learning is pretty straightforward. You first determine a set of learning goals that really identifies what students should achieve. And usually that is in the form of more what they should be able to do. Because if you're wanting to teach active learning, it's not just about answering declarative content questions, but actually being able to do stuff like scientific research. So the second step is to develop assessments for those learning goals. And that's pretty critical, because if your assessments are multiple choice questions, that's not a very good way of assessing what students are capable of doing. And especially when students realize that they're just going to be assessed with multiple choice questions, that changes the way that they learn. So you want them to the extent possible, you want them to know that they need to be able to actively engage in these processes, and that's how they're going to be evaluated. So the next step is to create educational technology to teach those learning goals. And then when you develop that technology, you deliver it, you deploy it, and evaluate it using the assessments. And then you iterate if necessary, and it's almost always necessary to iterate. So that's a critical process, and that process probably looks like the scientific process, because that's exactly what it is. Those learning goals and assessments are hypotheses, and then the educational technology, those are the experiments. So you develop a hypothesis, you develop a theory, you test the theory, and then you iterate. So within biology, there have been several calls from nationally sponsored groups like the Association for the Advancement of Science's Vision and Change report in 2011, and the National Science and Technology Council. And three high-level goals that they proposed were, number one, promoting the broad integration of computational thinking into STEM education. Two is one that is that the Vision and Change report put a lot of time into elaborating skills and big ideas that were important for students to understand, not just minutia. And third, more and more people are just taking us as gospel, because it is active learning is crucial for deeper learning. So in the next slides, we're going to talk about
until the bus.
Sorry. In the next slides, we're going to first talk about computational thinking, and then information flow and how that's related to computational thinking, and then how to teach these ideas using an agent of transfer in the form of a symbolic representation that in the form of a symbolic representation to represent information flow. So, so what is computational thinking? The the basic idea behind computational thinking skills is computational thinking is a problem-solving approach that involves breaking down complex problems into smaller, more manageable parts and using logical and algorithmic techniques to analyze how to solve them. It's often done with the aid of computers, but there's plenty of value on learning these skills independent of the use of computers. So just as a simple example, I thought I would present how you might apply computational thinking to trip planning, just to make this a little bit more concrete. So the first thing that you would do if you wanted to teach someone how to plan a trip, you would decompose that into a series of abstract components that they need to engage in order to have a successful trip planned, right? You need to lay out the transportation, whether you're flying or driving or whatever, your accommodations, the itinerary, the things you want to do. You need to budget funding and figure out what documentation you might need. So, I mean, this seems very obvious to everyone here, and this is kind of part of what Albert was saying before about getting past the minutia. You know, if you've ever planned an international trip, you know how to do this. So, but this is computational thinking, and in simpler domains, it's obvious. It's a little bit more. It gets a little bit more complicated when we look at harder domains like biology. So, 1, 2. I've got a panel blocking the bottom part of the slide for me, and I want to move that. Well, anyway, so let's talk about applying these computational thinking strategies to theories in the biological sciences. The Vision and Change report talks about information flow as being one of the big ideas, but I would argue that that's kind of the biggest idea. So if you apply the core computational thinking skills of decomposition and abstraction to biology, the most abstract level, the most abstract way to think about biological theories as pathways, and then a lower level, that's kind of the forest level view of biological theories. And then the mechanisms that implement those pathways are kind of the tree level. So a pathway, we'll look at that in a bit more detail shortly, but a pathway is basically just a series of processes, a series of steps, a series of interactions that need to take place in order for some higher level phenomena or phenotype to be able to be achieved. And so as an example of how scientists think about pathways, and you can actually analyze a system just at the pathway level without thinking about the mechanisms at all. For example, geneticists studying developmental pathways in worms, and this led to a Nobel Prize. They used radiation or some mutagen to generate a bunch of mutations, a bunch of different strains for worms, and then by crossing them, they were able to order the mutations in the developmental pathway and determine the causal connections, whether they were activating or inhibiting. And an activating influence is kind of more or faster or something that causes something to happen. And the inhibitory relationships are kind of stopping something, slowing it down. And so by crossing these different strains and looking at the resulting phenotype, they were able to order the mutations in a developmental pathway, knowing absolutely nothing about the mechanisms that implemented them. And that's still stunning to me, that you could learn that much about the flow of information in a developing organism as tiny as a C. elegans, a tiny little worm that you can barely see without a microscope. And then you leave uncovering the mechanisms for later. And so by laying that out, you break the problem down and you can focus on the individual steps and figuring out what the mechanisms underlying those, what those mutations are actually modifying until later. So in the biological sciences, there are two basic kind of competencies. Well, three particularly important ones in the biological sciences and any STEM field. First, of course, there's the scientific method, the process of science, scientific inquiry skills like designing experiments, collecting and analyzing data, drawing evidence-based conclusions. But then to help doing that, there are two kinds of reasoning that you engage in. There's quantitative reasoning, and those are skills that are more commonly taught, doing statistical analysis, analyzing graphs and charts and things. But the qualitative modeling and simulation is much less commonly used. So modeling and simulations are key tools for understanding complex biological systems that students need to be able to explore and develop on their own to really understand what the practice of biological sciences are all about. And that's also, it's the qualitative modeling that is much more relevant to computational thinking. So quantitative reasoning tends to focus more on the mechanism level, the lower level abstraction, and qualitative modeling is more at the pathway level. You know, when you describe how transcription and translation works, that's at the flow of information level. That's at a higher level abstraction. That's a qualitative description of the theory that doesn't get into all of the details about how the mechanisms work so much. So again, I've talked a bit about how there are these two components to theories in the biological sciences, the mechanism level and the pathway level. Now, one of the things that is really important in applying computational thinking to the pathway level is you need a representation for representing it more explicitly. So the pathway level focuses on information flow, emphasizing the interconnectedness of the different mechanisms, emphasizing computational concepts like conditionals and feedback loops and hierarchical structuring and control of information flow in these systems. So having a symbolic representation that helps you understand that is important. I'm going to skip this. So this is something that you could go back to and look at. So it goes into sort of what pathway analysis is good for, how it's used for understanding, developing theories, how it applies to medical sciences. But anyway, so back to symbolic languages. So what symbolic languages in STEM allow you to do? They simplify complex concepts and allow you to focus on the things that are most important. They highlight more important concepts. They ensure precision and support computational thinking. So again, they distill ideas for clarity and employ standardized symbols that facilitate communication, aiding in modeling, problem solving, and again, just visual clarity and conciseness for comprehension and communication. So they can also act as a bridge between different disciplines. So let's get a little bit more concrete about the biological pathways in the biological sciences and how to represent them. All biological systems can be represented. This is my claim, and I think that it's would be interesting to have a debate with some biologists that understand the field a lot better than I do, but the ones that I've spoken to agree with me about this. All biological systems can be broken down into one of these two or a combination of these two pathways. So you might imagine a factory that is a collection of assembly lines, and assembly lines build stuff up and break stuff down. In an auto plant, that's obvious what they're building up. In biological systems, you have anabolic and catabolic pathways for building up proteins that you need, breaking down energy sources. And in the way that assembly lines are represented in biological systems, those green boxes are gene products. In most assembly lines, the gene products are enzymes that catalyze different reactions. So you have a substrate, a product that's being moved down the assembly line, and those links connecting the nodes are things like other proteins or food sources or things that the cell needs, structural components, etc. The links between those nodes, the arrows are activation links, and the bar links are inhibitory links. And that's one of the things, those relationships between the elements in the assembly lines are one of the things that gets abstracted and made more uniform. And so students learn how different mechanisms, different activation and inhibition processes get implemented at the mechanism level as part of their study. The second kind of pathway are signaling pathways, and signaling pathways are the hierarchical control systems that sit on top of the assembly lines. For example, turning on and off the production of the enzymes that are needed in the assembly line. And the things that get passed down signaling pathways, it's just information. There's no substrate. It's just the state of the system, whether something is supposed to be, whether some process is supposed to be turned on, transcription, or some other process like that. I'll pause here to ask Albert if I've completely lost people. Do you want to add anything, or are there any questions people might have? Albert?
I was
Albert,
giving everyone an opportunity if they have a question. So
I was thinking
let's,
you went to sleep.
no, I'm extremely intrigued, and you know, I love your talk. I think it's excellent.
Um,
So let's see whether anyone has any questions first.
I should point out briefly that I'm trying to present something in minutes that normally we take weeks to present to students. So it's both hard for me and it's also especially hard for you guys. So there's, you know, and when I first presented this idea, people kind of thought I was crazy. Like, you can't teach this to students. But using cognitive tutors and doing it gently, active learning by doing, it is remarkable. And people have really been stunned at how effectively students can learn this stuff. So again, let me pause and see if there are any questions.
And from my perspective, I think you're doing an excellent job, Ben. I think it is you are covering very foundational, so I think everyone should have an understanding.
If this is working, then everybody else is doing a good job too. So just pausing to reflect on those assembly lines and signaling pathways again. So this is like algebra in math class. This is pathway algebra is an algebra. So if you think how in algebra in math class, you're learning how to represent word problems, you're learning how to represent things in the real world in an abstract formal way. Then you learn a procedure for reasoning about those quantitative relationships and solving problems, again, quantitative problems, and then you translate back out of the algebra equations and you have your problem solved. Pathway algebra is very similar. You're summarizing, you're formalizing these abstract relationships in a qualitative causal language, not quantitative, but a qualitative language for describing processes. And that can allow, and that can help you understand things like whether the presence of some input is going to turn on or turn off a phenotype, or turn it up or turn it down. If you have two inhibitory links, what do you get when you with a double negative? If you inhibit some inhibitory process, that becomes activation. And you know, you can these expressions effectively formalize an abstract statement about a biological theory. So if you're getting data and trying to understand it, this can serve as a very important way to summarize the data that you have. So again, there's a dynamic component about using these languages. You can summarize content. You can, as data is coming in, you can piece together a theory of the data that you have. You can organize complex biological interactions and see the results of these very, very quickly and easily, and use it as a tool to share ideas. Scientists use these kind of representations commonly in publications, so you can use them for communication and for sharing ideas. And when students get introduced to this pathway algebra, initially, the only thing they're doing with it is reasoning about a system like a genetic regulation system that they know, that they have complete knowledge of. But ultimately, when you start using them to try and develop your own theories of data that you're presented, you're not going to be able to rely on the theories, the symbolic expressions of the theories of the data that you have as being complete or correct, right? So it's a very powerful formalism that you can introduce and become comfortable with as you're learning the minutia, the initial content of biology, and then it becomes more useful and more powerful once you're familiar with this, and it becomes second nature. Then you can use it for summarizing theories that you're developing. So back to the science of learning. How can you use how can we develop learning goals? We want to develop learning goals for reasoning, for doing computational thinking and reasoning with an explicit language, symbolic language, for reasoning computationally about biological systems. So at the first level, you have, the students they need to learn about activation and inhibition, and how different kinds of mechanisms, like binding, you can have an enzyme that breaks a complex molecule into two, either activating the individual components or making it no longer function, or making it possible, blocking it from crossing a membrane if it's bound to it. So there are all kinds of different ways that you can activate and inhibit causally processes in a biological system. So, and then more importantly, stepping back, there are two classes of skills. So there's reasoning within a pathway algebra model that you've been given, or that you kind of summarized. So analyzing known pathways where the theory again is complete and correct. You can use those models, those pathway algebra expressions, for doing either prediction, reasoning from a given to what the outcome or the data would result from that, or you can use them to reason backwards to try and explain what might have led to some observation that you've seen. And then beyond reasoning within a model that you've been given, you can, just in the same way that for algebra word problems, you can translate a complex verbal problem into a pathway algebra expression and reason about that, and then translate out of it. And also, if you are generating your own theories, you may come up with a high-level characterization of the information flow, and then that can guide the instantiation, the refinement of that high-level flow of information diagram into the mechanisms that can guide the search for the mechanisms that implement those high-level abstract statements. So these learning goals, and this was, I should say, that the ideas that I've had about pathway algebra and using it for teaching computational thinking have been evolving over the last couple decades as we've been developing some educational technology to teach them. And the educational technology is in the form of a cognitive tutor, that they're also called intelligent tutors, but that's a little bit of a misnomer at best. Hopefully they are intelligently designed. There's a little bit of AI in them, but mostly the AI comes in trying to make guesses about what students know based upon their behavior within the tutor. But anyway, so the basic idea behind a cognitive tutor is that you scaffold a problem, you decompose it into a series of steps, and you instantiate or scaffold those steps with a text field or a combo box pull-down menu that allows students to solve step by step the problem that is in the particular that you're developing. And as they do that, as they answer steps in the problem, they get immediate feedback, immediate correctness feedback. Correct answers turn green, incorrect answers turn red. And you also can design it so they get more than just correctness feedback, but you can get hints to help you think about how to answer a question, or you can get correctness feedback, bug messages that give you a deeper explanation of why what you did was incorrect. They can be designed so based on the tutor's assessment of what you know and don't know, you can change the problems that you're given more introductory elementary problems, or get advanced to harder ones. And eventually the idea is to have students solve problems within the tutor until they reach cognitive mastery, until they really know how to do everything, and then they get to move on to the next topic. So let's look at an example cognitive tutor lesson. So this is a lesson that teaches assembly line, the logic of assembly line pathways. So you can see on the left in that red box, you've got some description of the level of the concentration of some protein and a particular mutation, in this case, a mutation in gene 3, and the low levels of ERA leads to the product for gene 1, which is a signal in a signaling pathway. Remember, it's just the molecule, the signals in the pathway being on or off. So you're told that if you've got low ERA, that's off. The next step in the pathway is off. And because gene 1 inhibits gene 2, if gene 1 is off, then the signal in gene 2, coded for by gene 2, is going to be on. And you move through that pathway. And in this case, there's a mutation in gene 3 that is a loss of function mutation. So it is gene 3 cannot be turned on. So it is always in the off state. In cancer, for example, cancer is a disease of signaling pathways. So the cell loses the ability to control cell proliferation. So if you have loss of function mutations that tell the cell to stop dividing, that's going to increase cell proliferation. So anyway, so at the bottom, you see the hint window, and then there's a yellow button with a question mark on the right. So if the student doesn't know what to do, they click the hint button, and then the arrows in the hint window allow you to move to deeper levels of help, and eventually highlights. So it's giving a hint on that bottom combo box, which is highlighted in yellow, which is asking what is the impact of a loss of function mutation on the resulting phenotype. Anyway, so there's an example. And so in the tutor that we've developed, we don't have very much support for assessments, for skill assessments. That thing at the top right is called the skillometer, and that gives an estimate of the tutor's assessment of whether the student knows how to perform the individual skills associated with this lesson. So the only skill that they've mastered is that one 3 up from the bottom, which is turned green. So that the tutor thinks that the student knows how to do that. They know how to reason about the impact of an inhibitor in an inactive state. So I should say that this lesson is an example of reasoning forward reasoning or prediction in a signaling pathway. The next lesson, this is an example of backward reasoning, where you're trying to infer or construct a pathway. And at that top blue box, the student is given a collection of mutants in C. elegans, a worm. And the first thing they do in the P1 step is determine whether the mutations in each of those mutants activates or inhibits cell death or apoptosis. And then once they do that, they cross the strains, they cross, say, strain Q, that first line in P2 in that blue box, they've crossed strain Q and strain R, and the worms that result from that have the phenotype of the R strain. So that tells you that the mutation in the Q strain occurs upstream of the mutation in the R strain. And again, this is very abstract, but the guys that worked out this analysis and applied this to several developmental pathways in worms, they got a Nobel Prize for it. So, we're reducing an extremely complex process, a Nobel Prize winning problem-solving exercise, into something that students can learn in a few hours. So, I mean, that's kind of neat. And we've actually introduced this, given the declarative instruction that talks about the discovery and what they knew going into this. And students do a remarkable job when it's presented gradually, and then they get a chance to work with a tutor like this. They develop a remarkably deep understanding of how that reasoning works. So next, another kind of signaling pathway, cancer pathways. And this, so this is, again, also signaling pathways, not assembly line pathways. This diagram is something that, that I'm very proud of, because I spent weeks reading cancer journal articles, understanding the different kinds of pathways, the different kinds of mutations that are common in cancers, and breaking this down into the diagram that you see, which even now it looks kind of complex, but what I was starting from was just unbelievably overwhelming for me. So that's a representation of the cell. That top line is the outer cell membrane, and those green boxes are code for proteins that are membrane-bound proteins that are embedded in the membrane of the cell, and they serve as they enable signals from the outside, for example, hormones or glucose. So in glucose metabolism, there would be a membrane that insulin would bind to, and that would open a channel that allows glucose into the cell, where it's then transferred to the mitochondria, and the Krebs cycle turns that glucose into ATP that the cell uses for energy. So again, the membrane-bound proteins at the top, and then the other signals. And then at the bottom, you have the nucleus, where those signals get translated or transduced into turning on genetic modules within the cell, turning on, creating proteins that are needed to respond to those external signals. So anyway, cancer at a very high level of abstraction. Again, this is computational thinking, so we're trying to break this down. Cancer involves damage to two common genomic modules: the cell's accelerator and the cell's brake. The cell's accelerator are cell cycle pathways that tell the cell when to divide, when to multiply. And the cell's brake is the apoptotic pathways, which tell the cell if it gets damaged. There are signals that recognize that and signal protein by the name of P53 that the cell's been damaged, and that directs the cell basically to commit suicide. So what happens in cancer is the cell cycle pathways, the accelerator, those cells have gain of function mutations. Those pathways get locked on, and the cells brake, the apoptotic pathways get loss of function mutations. They get turned off. So, the metaphor is, if you're in a car and the accelerator is locked on and the brake no longer works, you're going to get a lot of uncontrolled behavior of that vehicle. So in the same way, when the cell cycle is locked on, so the cells are growing and growing and growing, and the apoptotic pathways that can stop that are broken, then you're going to have uncontrolled cell growth, and that's going to lead to cancer. So that diagram, after I put so much work into that, we used that for creating two lessons, a forward reasoning lesson and a backward. This is the forward reasoning lesson, where in the red box at the left, the student is given a collection of mutations in signaling nodes in those pathways, and they then interpret those, whether a gain of expression in some, they characterize the mutation, and then they determine what impact that's going to have on which of the two pathways, cell cycle pathways or genes, or the apoptotic genes. Then they determine the change in activity of the cell cycle or the apoptotic pathways, and then summarize that into the impact that it's going to have on cell proliferation. So if, for example, if all of those highlighted mutations contributed to accelerating cell proliferation, then that could potentially lead to cancer. Here's a simple example of an activity that's not part of a cognitive tutor, but part of a similar kind of learning by doing activity within OLI, the Open Learning Initiative. That's the platform that hosts all of these courses. But so OLI activities give a similar kind of question that you can ask, but these are embedded within the text. The cognitive tutor lessons are kind of something that you do for solving problems after you read the chapter of text. And these activities are things that you do that are sprinkled within the text as the student is reading the content, so that they don't fall asleep or just skip over what I used to do when I was learning. When I was taking class, I would just blow off reading the material, and I would skip ahead to the problem solving at the end of the chapter, and then kind of use that to go back and try and find what I needed to do. So this kind of discourages students from doing that. It gives you a more complete understanding, and you can of course still do what I did. But anyway, so this activity is looking at two genes, gene A and gene B, in a pigment pathway, an assembly line pathway. So gene A converts a white pigment to pink, and then gene B inhibits that. So the student is asked to determine what the phenotype of each of the four, the technical term is true breeding strains of flowers that have those two genotypes. So again, as they determine the phenotypes, white or pink, they get correctness feedback down below, and then they're asked to determine, to kind of summarize how when you get a white flower instead of a pink flower. And again, of course, correct answers turn green, incorrect answers turn red. You have a help button and you have feedback. And this, so these, when you scatter these things throughout a chapter of text, that gives you a formative assessment of what the student knows, what they're having trouble with, as they're reading the material you've given them, right? So you have, and then in OLI, you can also develop summative assessments, quizzes at the end of the material, but so ultimately you want to have a collection of different assessments, both during the learning process and then after the learning process. And between cognitive tutors and activities like this, at a range of tools in your, or weapons in your arsenal for developing education technology. So then the cognitive tutor for pathway analysis currently only gives students, they only reason within a given pathway that's complete and correct. Okay, it may be broken, but at least you know what the pathway is. I've been moving beyond that, coming up with activities to teach students to translate into pathway algebra. Both the way that we're doing this initially, the way that I see this working initially, is that as students are reading a chapter, they would be generating their own summaries of what they're reading about as pathway algebra statements rather than just being given them. So you can imagine if you were continuing with the metaphor of or analogy with high school algebra, imagine if you were given a word problem and then just told, here's the equation for that. That would be kind of only giving you part of the skill set that you needed. You actually need to be able to translate word problems into the equations, because in the real world, that's what you're going to need to do, right? So this translating into pathway algebra, first, is a way of summarizing, translating out of pathway algebra as a way of incorporating your answers to what's going on in the verbal description of the world, and also translating out of as a way of trying to drive the refinement of these high-level abstract relationships into a mechanism level description. There are different types of experiments that you can use that would help tell you what the mechanisms are that are characterized in those high-level diagrams that you generate from a different kind of data, like we saw in the backward developmental genetics tutor problem. So to help with the translation part of this tutor, I've been developing what I call a MERS library. MERS stands for multiple external representations. So you can imagine you're reading a journal article, or you're reading a chapter in a biology text, and that biology text gives you a verbal description and a diagram. And so I imagine that the students would be given the first two of these representations, the diagram at the top and then the text in the middle, and the student would be asked to generate the pathway algebra summary at the bottom. Now, you know, when I was reading complex journal articles, you know, the way I learned biology, I would just start reading crazy insanely difficult things that I didn't have an understanding of the prerequisite content. It was a very interesting way of trying to learn biology. And I found myself trying to generate summaries. I would have these documents where I had progressively more. I would start formalizing the language first and eventually get down to something very much like those pathway algebra statements. We could go through, Albert, I don't know if you think it would be worthwhile to go through. So this is an example of a self.
Yeah, I was going to let you know that we're running low on time.
Okay, so this kind of it's I tried to make this example as self-explanatory as possible, so you could go back and look at that. So then with the MERS library, with the collections of these different representations, you would create, the idea is we're going to start creating these activities where we give students a textual description of some pathway, and then they need to generate, or in this case, select from a combo box at a first level of approximation. That's kind of I'm not really happy about that, as it's kind of doing too much for the student, but it's doable and tutorable, and we can evaluate that and see how well it works. So in this case, the student gets a statement like, normally, cyclin D3 initiates transcription of cyclin E. Cyclin D3 binds to CDK4 to inhibit RB1 by phosphorylating RB1, which frees up E2F. Free E2F enters the nucleus and binds to the DNA acting expression of cyclin E. So if that seems like really overwhelmingly complicated, that's good. That's why you want to be able to summarize a statement like that into a pathway algebra expression. So we broke that paragraph down into two chunks of pathway algebra. And you start, it actually works better if you kind of start from the end, the end process, and work your way back in generating the pathway algebra. So there are two chunks highlighted in yellow from that text. Excuse me. And then that list of chunks of pathway algebra text those are menus, and then the green answer highlights the correct one. So this is an example of a design for a lesson to teach students to translate into pathway algebra statements. So there have been a bunch of people that have been working on this. As I say, it's almost 30 years old. So the two main people that I worked with on the first 25 years were Albert Corbett, the cognitive psychologist, who was the PI on the grant, and then Linda Kaufman, who was a biology professor, and she did a lot to teach me what I know about biology, other than reading journal articles, etc. So those were the developers and designers, people that I've been working with. We've been introducing this to AP biology students in both mostly private high schools. Mark Krotek at Central Catholic in Pittsburgh has been working with me for more than 20 years, probably 25. Edwina Kitchington teaches AP biology in a public high school. Becky Gonda is the director of community outreach at the University of Pittsburgh, and she is the curriculum developer, and she teaches teachers to teach something called college and high school, which some of you may have heard of. It's like AP biology, but the thing that's wonderful about CHS biology is that we have control over the curriculum and the assessments. So that is fantastic, because as you know, from the science of learning, you have to be able to determine the learning goals and the assessments. And then, so if you're not in alignment with those, you're going to run into trouble. So we figure we'll get CHS using the tutor first, and then we'll try and break into the AP classes where we have less control and where the standards are set at a national level. And of course, the latest additions to this enterprise are Albert and Sherma at Bethune-Cookman. And we're hoping, I don't know if we've got any biologists in the audience, but I'd love to talk to any biology professors that are out there and see if, I'd be glad to discuss this in more detail. And if anybody's interested, it's easy to sign up for an account on OLI and to get access to the tutor. And I would love to see this as a starting point in a longer conversation. So I would almost be disappointed if I don't hear from some of the people out there in the audience. Maybe we can do that more efficiently if Albert we can arrange another Zoom meeting or 2 or 3 to discuss this. Anyway, I think that we're close to the end here. So again, we've tried to take the principles of computational thinking, of decomposition and abstraction, and apply them to biological theories, and to develop a symbolic representation for the highest level abstraction of pathways, and to develop a cognitive tutor to actively teach students to use models and ultimately to build their own models. So that's all I've got to say, and I hope there's some questions. Thank you all very much.
Before, I'm not sure if anyone has any questions, but I just wanted to say we are going to continue the conversation with Ben. Within a couple of days, you will receive a correspondence about our Journal Club series. And so the Journal Club series is kind of a continuation of this. We're going to have some articles from Ben on this same topic. And in that Journal Club, we'll have time to have further discussion on these topics, more examples, more detail. So if you do not, if you still need to process more before you ask a question, that's a perfect example for that. So like I said, please be on the lookout for that email and that correspondence so you can register for our Journal Club series.
And I can make the slides available for people, and I would be more than happy to answer questions. It would be probably good to share them in some sort of public forum, maybe via email.
Yeah, I got. So
whatever works for people.
Yeah, so I got it. So the presentation, so Ben will send us the presentation. The presentation and the recording of today's lecture are going to be on the website, the same website that you went to register. That is the Science of Learning Network website. So please, if you have not, please bookmark that website. Every lecture will be there recorded along with the supplemental information. So that's where we're going to put that.
And I should also say that I see this is a talk that I've been effectively working on for years, and I eventually want to morph this into a presentation more for students. So take out some of the stuff for Science of Learning Center and put in more instructional stuff. So questions that people have of all kinds would be helpful for that process, and I would be more than delighted to have people actively engaged. There we go. That's active. The buzzword. Actively engaged in thinking about a mental model for the biological sciences and how to use it for instruction. Thanks.
Any questions currently? Right. Well, thank you all so much for attending the first lecture in this series. Please be on the lookout. We will have additional lecture. There is a lecture next month, so please be on the lookout for the advertisement for that and the registration for that series. We will also have another lecture in November, so we will have one every month. It will continue into the spring semester as well. So we appreciate your attendance. We look forward for your participation in this network. Have a wonderful day, everyone.